Almost every atom in chemistry starts out with a problem. It is inherently unstable. To fix this, it will interact, bond, and modify itself to reach perfect stability. This diagram breaks down the two terms you need to understand that process. Valence electrons are simply a static count of the electrons an atom possesses in its outermost shell. That is what you have. Valency describes the actual behavioral action the atom takes to become stable. That is what you use. We are going to learn a mathematical shortcut to calculate both of these numbers instantly, but we need to establish a strict boundary. This method only works for the first 20 elements on the periodic table, from hydrogen straight through to calcium. Within these first 20 elements, we have three anchors: helium at atomic number 2, neon at 10, and argon at 18. These are the noble gases. These three noble gases are perfectly stable because their outer electron shells are completely full. They don't need to do anything. Every other element in the first 20 is simply trying to modify its own outer shell to mimic one of these three. So predicting how any atom from 1 to 20 will behave chemically is just a matter of calculating the easiest path it can take to look like one of those three stable anchors. This formula calculates your starting inventory. To find an element's valence electrons, you take the target element's atomic number and subtract the atomic number of the noble gas that comes right before it. Let's test this on sodium. Sodium has an atomic number of 11. The closest noble gas that comes before it is neon at 10. 11 minus 10 gives us 1 valence electron. This seesaw illustrates our transition to valency. Sodium currently has 1 outer electron, but it requires 8 to reach a full, stable shell. It has 2 possible behavioral paths. It can lose that single electron, or it can attempt to gain 7 new ones. Dragging in 7 new electrons costs far more energy than simply shutting 1. Atoms will always take the easiest route available. Because losing 1 electron requires so much less energy, sodium will always choose to shed it. Therefore, its valency, its combining action, is exactly 1. This same logic holds for magnesium with 2 valence electrons, aluminum with 3, or carbon with 4. Because shedding these smaller numbers is always the lower energy path, their valency perfectly matches their valence count. Let's put this to the test. Hit the pause button and calculate both the valence electrons and the valency for chlorine, which has an atomic number of 17. Use your 3 anchors. Atoms are fundamentally lazy. For any element with 5 to 7 valence electrons, valency is the calculated deduction of the energy cost required to reach the number 8. This equation reveals the first half of the solution. Chlorine is 17. Subtract the previous anchor, neon, at 10, giving an inventory of 7 valence electrons. To reach 8, gaining 1 electron is vastly easier than losing 7. So chlorine's valency is 1. There is one edge case, the noble gases themselves. If you calculate neon, which is atomic number 10, its previous anchor is itself. 10 minus 10 is 0. It is already at its target, so its valency is 0. This split-screen graphic summarizes the entire framework. On the left is your mathematical shortcut for finding an atom's starting inventory. And remember the warning at the bottom: do not apply this beyond calcium. On the right are the behavioral rules. 1 through 4 means the atom loses electrons, so the valency matches the count. 5 through 7 means the atom gains electrons, so the valency is whatever it takes to reach 8. 8 means it's fully stable. Valence electrons dictate the static inventory an atom starts with. Valency represents the exact calculated transaction it must execute to reach a perfect 0 or 8.